Okay, lecture 5A, people. The numbers will not go higher than that. Areas between curves. Okay, again, this is our final topic lecture. Welcome. We're going to talk about areas between curves. And I'll end with an example from economics, which we don't usually do. Okay, soon after we started this unit, we started talking about areas and areas under curves, which is our attempt at tackling a problem, an ancient problem that we started discussing in the first lecture, the area problem. We approximated the areas using Riemann's sum, so we summed up areas of rectangles, and then we took the limit, and we arrived at an exact answer, a definite integral. And then we discovered the fundamental theorem, which told us how we can evaluate that using antiderivatives, in many cases. We also found the fundamental theorem gave us a way to interpret the definite integral as an accumulator of change. And finally, last class, we talked about how a simple change of variable can make our lives easy and make an ugly-looking integral look doable and be doable. So our final topic now is going to be another area problem, but not this time the area between a graph and the axis, but between two curves. Hence, area between curves. So, picture. I may need a color. Okay, I'll try pink, and y'all will tell me if you can't see it. Okay. From A to B. This is the x-axis. I won't draw the y-axis, so you don't know where this thing is. Can you see pink at the back? Okay. All right. Good. Let's say that's F. Let's say pink is G. Okay. And suppose what we're after, shockingly, is this area. Okay. Okay? We're looking for the area of the region that's bounded by y equals f at x, y equals g at x equals a, and x equals b. They bound our region. We're looking for the area inside there. We're looking for that area. I'll just write that. We want the area of the region bounded by x equals a, x equals b, y equals f at x, y equals g at x. Okay. Furthermore, suppose that throughout, guess what I'm going to say, throughout AB, f and g are continuous, so nothing weird happens and we don't have to think too hard, and f is on top. Everything's nice and joined up, and f is on top. Okay? As drawn. Alright, now what we could do is we could chop this thing up into slices, approximate the area of each slice by a rectangle, get a Riemann sum, add them up, that's the Riemann sum, take the limit, and we get a definite integral. Okay? I'm not going to do it exactly like that. I'm going to do it using a sort of sloppy, more intuitive, direct approach that I've mentioned before, but it can just be turned into the Riemann version. Not very different at all. Okay, so look at any particular value of x, okay, say there, okay? And there we look at a thin slice, an impossibly thin slice of this thing, okay? So the value of x, a particular value of x, we look at an impossibly thin slice of our region. Okay. Good? Now, impossibly thin. Its width is infinitesimal. Okay? Really tiny. I said that as we go in the limit, we can talk about impossibly tiny widths. And again, that's sloppy, but let's try it. Okay? So really, really tiny width dx. The height of this slice, which looks essentially like a rectangle because it's so thin, an impossibly thin rectangle, its height is given by the top value minus the bottom value. So the height is f at x minus g at x. Okay? So, the area of that impossibly thin slice is base times height, or height times base. Okay, so that's the area of our impossibly thin slice. That's our impossibly thin width, and that's the height of the rectangle. Now what do? We add up. We run along the continuum from A to B, and we smoothly add up the areas of all these impossibly thin rectangles. Smoothly. Running continuously from A to B, we add up those areas. And there you go, you got a definite integral right away. Okay, nice, intuitive, easy. Okay, or you can do this the rigorous way, the standard way. You build a rectangle of width delta x, add those areas up, get a Riemann sum, take the limit, get a definite integral that way. Okay, I've mentioned this chopping up into slices thing multiple times. First when we talked about area the first time, now when we talked about displacement under a velocity time curve, when we talked about distance. This is a useful thing, and I might bring it up again. So this idea of chopping things up is incredibly important and leads to things like definite integrals. Okay, good? That is the area between the curves. People, hey, look at that. Equals. Okay? This is the left endpoint of the interval. This is the right endpoint. This is the top curve. This is the bottom curve throughout the interval. Okay? All good? Okay. Okay. Another way to look at this real briefly. Which may make you feel better. Okay. Let's suppose also that everybody's non-negative. So f and g are non-negative on the interval. Okay, in other words, they both live upstairs, so they look like this. Okay, and we're after the area between them. Okay? The area between is just the area under F minus the area under G. Okay? That is that minus that. So the area between is equal to area under F and above the x-axis minus the area under G and above the x-axis. Okay, since everybody's non-negative, area is the same as signed area, it's the same as the definite integral, we can just write this. Integrate from A to B, F, and subtract this guy, the integral from A to B, G. We can break up sums and differences, we can also bring them together. Surprise, surprise, same result. Okay. Top minus bottom, integrate over the right interval, and you've got the area between the curves. I said this as if they're non-negative. Honestly, if they weren't non-negative, suppose stuff was going on down here, I could sort of imagine shifting them up, and that lets you sort of extend this result. Okay, so this is more general than it looks. It can actually, stuff can be down here. I can move things up. And because if I shift both the curves up by the same amount, the area between them isn't going to change, and this thing isn't going to change. This extends to the general case too. All you need to know is this. Questions? Example. I may or may not have mentioned this before when Leibniz was talking about integrals in the first place and derivatives in the first place. He was talking about things like this, infinitesimals. Which for us is a sloppy way to talk about things. Okay. Example. Compute the area of the region bounded by x equals 1, x equals 2, y equals reciprocal x, and y equals e to the 1/2 x. Okay. Don't write an integral right away. Picture the thing. See where your region is. See where your boundaries are. So. Make this bigger. X, Y. Okay. We want to go x equals 1 is one boundary. Okay, it's 1, 2, 3, 0. So that's x equals 1. Okay, x equals 2 is another boundary. Okay, the other guys. This guy's got a branch down here. It's not going to affect us. I won't bother to draw it. Okay. That's 1, that's 2. A rough sketch will do, but, you know. Okay. That's sort of y equals reciprocal x. And that is a rough sketch. And now we need to picture this thing. Growing or decaying?
Growing.
Thank you. Excellent. What's its y-intercept? 1 is good, thank you. Excellent. Okay. This guy cuts here. You can stick 0 into there for x. I think you'll see that. And let's see here. All right. Okay, and that guy, again, all rough sketches, is the other function. Okay, good? Okay. Again, rough sketches will do. We just want to see what this thing roughly looks like. And there's our region. Our region is this thing. Okay. We want to go from 1 to 2. Okay, so those vertical boundaries give us the limits of our integral. Okay, so let's just write this. Okay, the limits of our integral are 1 and 2. Given by this, write this however you want. I just want to make a point that you note two things. The limits of the integral are this guy and this guy, and now we need to find the integrand. Okay, so we need to know who's on top. Don't forget to check who's on top. Who's on top? Pink. Who's on top? Okay, you can make a computer plot, you can make a rough sketch, you can do some other sort of analysis. You could think about this thing and realize that the pink guy is going to hit 1 when x is 0, and it's going to be increasing thereafter. This guy, you know, is going to hit 1 at 1, and it's going to be decreasing thereafter, and that should convince you that, yeah, pink is going to be above white in the interval we care about. So do something semi-intelligent to find out which guy's above. And now we're ready. And everybody's continuous. So the rest is just mechanical, depending on how comfortable you are with integrals. We go from 1 to 2, from here to here. Top minus bottom. I'll write that. Top minus bottom. That's it, we do that thing. And everybody has a nice antiderivative. Okay, what's this guy's antiderivative if you know offhand? 2 is good. I'll assume the rest. The 2 is what I'd be worried about. Okay. Excellent. How can you do this? Experience, and then you just say it right away, or you think it right away, and then if you want, you can check it. Okay, and if you wanted to check this, the 1/2 comes down, kills this 2, and we're left with this, which is what we wanted. Okay, so you could use the guess and fix thing. Suppose you guessed this, you'd have an extra factor of 1/2, you'd get rid of it by multiplying by 2. Again, you could just know it from experience, or if you're just totally flustered, you could substitute u for 1/2 x, use substitution, and that'll work just fine. Okay? This is what I meant when I said the easier kind of substitution. The easier kind of substitutions are the ones where the derivative is a constant. Okay, good? What's this guy's antiderivative? Ln is good. I'll do absolute value. Thank you. Occasionally it matters. Okay, take the derivative, you get this guy. And in fact, here this won't matter because these two guys are both positive, so if you put absolute value or not, you're going to get the same answer. Okay, and then we do this thing. 2e to the 1/2 times 2. It's not going to fit, is it? Okay. 2e to the 1/2 times 2 minus ln absolute 2 minus 2e 1/2 times 1 minus ln absolute 1. I'm 0, and I think nothing else is pretty here. Okay, 2e to the 1 minus ln 2 minus 2e to the 1/2. Write it however you want. We're good? Okay. And a calculator will tell you that's approximately 1.446.
So you're saying that approximately?
Depends on what the exam or whatever tells you.
Okay.
Yeah? Math folks like exact. But scientifically it's useless, often, right? Okay. There's a reason I don't have a definitive answer there. Once I do, I'll let you know. Okay? All right, excellent. If you're fussy about this kind of thing, and you say this is in units and this is in units, then you say the area is in units squared. I say that because the books insist on saying that kind of thing. Okay, our answer is not negative, which is good news. Okay, it's an area, it better be not negative. If you got a negative answer, one of the first things you can check is, did you get these guys flipped around? Did you think the bottom guy was on top and the top guy was on the bottom? So make sure you go top minus bottom. And that's that. Questions? Okie dokie. Are you really economical here? Compute the area of the region enclosed by the curves. Y equals 2x squared minus 4x plus 2. And the other guy is y equals 3x minus x squared. Okay. And you go, ooh, what the heck, there's no x boundaries. Exciting. Okay, remember I need to get a feel for where this region is, where the boundaries are and all this, so I'll need something like a sketch or a computer plot or some other kind of analysis to tell me where the heck anything is. And here a rough sketch does fine, so let's sort of rephrase these things so we can sketch them in some acceptable way, and then that's all we need. So, okay. This guy I could rewrite as this, factor out the 2. Okay, this isn't a real world example, right? In the real world you get ugly numbers. Sometimes it won't be easy to do some of this stuff. You might generate a computer plot, do something else. Okay, factor again. Okay, that looks like something. What shape is this, people? It's a parabola. Does it open up or down? Up is good. And what's its x-intercept? 1. That's it. Okay, good. What else do I want to say? Okay, good. So, what do we got? We got a parabola. Opening up. Opening up because this guy's positive. Or you could say because this guy's positive. What else? Kisses the x-axis at 1. And there's a vertical stretch by factor 2. This isn't to sicken you all with memories of sketching, it's to tell you that we need to picture this somehow, and this is how we picture stuff. When we can. Second guy, I'll factor out minus x, and then I get x minus 3 inside. Hey, surprise, it's a parabola again. So it's a parabola. No added stretch, but because this is negative, or you could say because this is negative, it opens down. And its x-intercepts are at 0 and 3. Cuts the x-axis at 0 and 3. Again, a rough sketch is enough. All you need is enough information to know where the heck your region is. Okay. I will do this guy first. Let's say that's 3. 3, 1, 0. Okay. So we want something that opens down, cuts the x-axis at 0 and 3, and that's it. No, that's not good. Looks great. Okay, and the other guy opens up. Where's my pen? Okay. The other guy opens up, it's still a parabola, it's stretched compared to that guy, and it kisses the x-axis at 1. There we go. Okay, the opening up one is that guy. Okay. All good? Excellent. Okay. And the reason we're looking for is this one. And the reason we didn't have to specify any sort of x boundaries is because these guys enclose the region. Where they intersect tells us where the x region is. Okay, for the record, this is not a symmetrical looking shape, okay? So because of the one guy being stretched and the other guy not, and because where they're positioned, this is not a symmetrical looking thing, just for the record. Okay. Okay, we need to find the limits. Okay, before we were told them outright and they wound up being where they should be. But now we need to look at where these things intersect. Okay, the intersections of the curves tell us the boundaries in terms of x of the enclosed region. Okay, so the curves intersect. Where what? Where those two guys are equal. 2x squared minus 4x plus 2 equals 3x minus x squared. Okay, we move stuff around. 3x squared minus 7x plus 2. Okay? And then I use quadratic formula because you just don't want to look at this, or you factor it. Okay? And you get that the intersections are at 1/3 and 2. Okay, so the limits are 1/3, 2, 1/3, and 2. Okay? Okay, the real world isn't always this nice, okay? So most things can't be factored. So what do? You stick them into the quadratic formula. You use Newton's method. You ask Wolfram alpha. You graph things and you zoom in and you try to find an approximation of what you're looking at. So find some dignified way of solving this thing, approximately if necessary. Okay? Or some other algebraic trick. Okay. Who's on top? White's on top. Okay, over the interval, white's on top. And that's it. We're all set. We can write our integral and end the question. the area is equal to, we integrate from 1/3 to 2. We go from here to here. Top, how do I write this? Top minus bottom. So again, top minus bottom. All right. Here we go. What do we got? Minus x squared minus 2x squared, so minus 3x squared. 3x minus 4x plus 7x minus 2. And I didn't write dx because I'm crazy. Good. All right. Good. Antiderivative.
Negative 3 over 2. Negative x 3.
Yeah, that's right. Okay, so negative 3 over 3, x to the 3, or just negative x to the 3. Okay. This guy?
7 over 2 to the x squared.
Excellent. Okay, crank the exponent up by 1 and divide by the new exponent. Easy peasy, and this is just 2x. Okay, I'm not going to spell this out because it's really boring. Okay, you plug the 2 into this thing, and then you plug the 3 into this thing, and you subtract the first one, you subtract the second one from the first one. Okay, and you get 125 over 54. If you like exact stuff, which is approximately 2.315. In square units, if you're that kind of freak. Okay, that gives us the area of that puppy there. Okay, and it's again not negative. That's good news. If it was, you'd probably check if you got the directions mixed up. And be a good person, write dx, because sometimes it matters a lot. And in this case, we had one of those ones where both of these guys were non-negative over here, and so really what we got was the area under this guy here minus the area under this guy here. But that doesn't matter. You just apply the formula, you get the answer. Okay. Questions? Yes, ma'am.
We generally have to plot the two functions to see which one.
You need to sketch something to know where anything is. Unless you've got a better way to do it, that's fine by me, all right? But you need to know where stuff is, that's all. If we ask you something to do. Okay? All right. I'm going to do an application from Econ, which we've never seen so far, which I've almost actively avoided. Okay. All good here, right? Okay. Okay, so it's an application of areas between curves. You don't have to worry about this. You can just listen or not listen if you want. Just don't talk over it. Okay, if you take microeconomics, you're definitely going to see this. It won't be written out as integrals, obviously, because those people don't know how to do integrals initially. Okay, so this is something you'll see if you take econ. Okay. Well, you heard of supply and demand. Can I just ask, is anyone taking microeconomics? Is that a thing people do? Brilliant.
Yeah, true.
Thank you. Very good. But if I make a mistake, I'm very rusty on this. If I make a mistake. Okay, we're going to talk about supply and demand. We like to draw graphs like this, which are kind of weirdly oriented, okay? So this is going to be the unit price of a good, this is going to be the quantity of the good. Okay, a product, oranges, books, whatever. Okay, again, you don't need to know this at all, I'm just trying to give you some kind of application. Okay, put the price here, the quantity here. We'll talk about demand first, okay? Alright, what do we do? Let's do something like that. That's called the demand curve. What is that telling us? That's telling us that as the price of something increases, the amount of it that people will be willing to buy or demand goes down. Okay? Now again, this is stupidly oriented for this discussion, but this is how economists do this. So again, the higher the price, the less people demand or are willing to buy. Okay? We're used to this. Not everything's like this, but almost everything is. Okay, and that's why this thing slopes downward. Okay, the other one is, oh look, there's pink. Okay, the other one, surprise, is supply. Let's do that. It's called the supply curve. Okay, the higher the price of something, the more of it suppliers or producers or manufacturers or whatever are willing to make, okay? So the higher the price, the more people are willing to sell. Or the more firms are willing to sell. And so that's why this thing is upward sloping. And that's all that says. Okay, and one thing you're going to learn in econ, if you take it, is that markets, free markets, competitive markets, tend toward equilibrium. Okay, and in this case what that means is that the price stabilizes to there. Okay, so that's called the equilibrium price. That's called the equilibrium quantity. By the way, microeconomics is essentially study of behavior. It's the behavior of firms and people in free markets. Okay. So the market settles toward equilibrium. The behavior of sellers and buyers basically pushes the market price toward here, toward where these guys intersect, where the amount supplied and the amount demanded are the same. Yes, ma'am?
I can't tell, but I think your microphone might have...
Really?
I mean, I'm in the front, so I can't.
How curious that the front row told me that. And very worried. Thank you. I should have like commercials ready to play during this. The idea of it dying 2 classes in a row is a bit weird, but there we go. Thank you. It's good now, yeah? Thank you. Excellent. Okay, good. So again, market forces, the behavior of people in firms, forces the price over here, okay, where these guys intersect, where the quantity supplied and the quantity demanded are the same. There's no shortages, there's no surpluses, nothing like that. Okay. Excellent. Now we talk about areas. Okay, check this out. So, the area between the demand curve and the price level. Anyone know what this is called? Good. Yes, that's it, thank you. Consumer surplus. Okay, in a way this measures the dollar amount of how much better off consumers or buyers are from this whole thing having taken place. Okay? For example, suppose I'm on this demand curve somewhere, and suppose this is about books, okay? And I was over here, and I'm willing to pay $20 or less for a book. Okay, if I'm willing to pay $20 or less for a book, and I managed to buy the book for $15, then I've sort of benefited by $5. Okay? So how much better off I am because of this sale can be measured that way. Okay? So I was willing to pay 20 bucks, I got to buy the thing for 15 bucks, so I benefited by 5 bucks. Okay? And that 5 bucks would be the difference between what I was willing to pay and the price that it was. So that amount. And if I add over all the people who were involved in that kind of thing, so all the buyers who managed to buy, then I get what's called consumer surplus. How much better off everyone is in a dollar amount altogether because this thing happened. Okay, similarly, producer surplus. The producer surplus. With an S on it. Same-ish kind of argument. The area between the supply curve and the price level is how much better off overall the producers are from this sale having taken place. And one of the big lessons of economics is in free or competitive markets, everyone's happy, right? Producers benefit and consumers benefit from trade, okay? The total area between the two curves up to here is called total surplus. Okay, so we get the area between the demand and the supply curve up to that equilibrium, we get what's called total surplus. It's how much better off, or how much everyone has gained net, producers and consumers, from trade having taken place, from sales having taken place, or whatever. Okay. Once we understand this, then we can talk about other things. We can talk about how does the position of this equilibrium, does the price hitting this equilibrium, how does that affect total surplus? Okay, could total surplus have changed if the price was different? What would happen if the price went up? Would consumers suffer, producers suffer, and all this kind of thing? Okay, just an introduction. Hopefully that makes some sense. So in economics, you do actually talk about areas between curves, and if you can model these things with equations, which does happen, and you find the areas between them, then you can discuss the effects of, let's say, changes in price or various policies and that kind of thing. What did we do? We did areas between curves. We talked about it when we have boundaries and curves. We talked about it when we're just given two curves, and we're asked to find the area they enclose. We find their intersections, we integrate between them. We talked about an application, which I hope you found understandable. And that is it. Okay? That's the last topic. That's the last subtopic. I'm done with topics. Monday, I will do problems. I'll say little sort of trivia about things, like things you really don't have to worry about. If there's anything I can tell you about exam coverage at that point, I'll tell you. And that's it. That's the last topic. I'm not saying goodbye to you today. I'll say goodbye to you twice on Monday. Thank you. I will try not to cry. Okay, thank you guys. Have a good weekend. I'll see you on Monday. And oh, yeah. If you want to evaluate me in class on Monday, please bring a computer, or a phone, or a magic wand or something. Thank you.